Hey there, this is Lucius Laframboise from ENG Suite, and today we are going to take a look at another normality test. Today, the Lilliefors corrected KS test. So the Lilliefors test for normality is a correction of the Kolmogorov-Smirnov test. It uses the KS statistic, but it uses a different method of calculating the associated p-value to make this test more selective and to make it more powerful. Power being the ability of the test to correctly reject the null hypothesis. Now, just like the KS test, the null hypothesis is that the data follow a normal distribution, and the alternative is that the data do not follow a normal distribution. So when we say that the Lilliefors test is a correction of the KS test to make it more powerful, we're saying that the Lilliefors test uses the KS test statistic, but it calculates a p-value that can correctly identify data that does not follow the normal distribution more often. But how does it do that? Well, we start with the KS test statistic, and if you remember from our video on the Kolmogorov-Smirnov test, the KS test statistic is the quantity of the distance between the actual data and the empirical distribution function and the expected, the cumulative distribution function. So it's the maximum deviation between that expected, that cumulative distribution, and the actual, the empirical distribution. So wherever that distance is the greatest. Then we use a p-value table and interpolation to calculate an associated p-value. Now, sometimes we can't interpolate. We have a p-value that's too high or too low. Then we will use an approximation algorithm to calculate that p-value. So if you remember from last time, and we'll just briefly go through this, the KS test statistic is the max of these two arrays here, which are just that's the deviation between the actual data point and the expected data point. So calculating the p-value, as I mentioned before, there are two main methods. Though in this case, we want to use the table when possible and only the approximation when interpolation is impossible. Then the first method is that p-value calculated through interpolation of values found in a table. We'll go through the interpolation process on the next slide, but it's pretty easy. It's just linear interpolation, very similar to what we did in Shapiro-Wilk. The second is using an approximation equation. Now, this method is only accurate to 2 decimal places, so 0.0x, so that hundredths place there, which is why we want to use the p-value table as much as possible, because we can get the actual values or a better approximation than using this approximation. So calculating the p-value using that first method, we're going to do an example here to show you how to use the p-value tables. So in this example, and our sample size equals 30, and our KS test statistic is 0.144165. So here's our linear interpolation equation where we use our P1, P2, and our KS1, KS2. And to find our P1, P2, first we need to figure out where our sample size row is. So we have this row here, and that is for n equals 30. And then we're going to check each of these KS values to find the one that is the largest lower and the smallest higher number. So 0.1315, that is less than 0.144. 0.1378, that's still less than 0.146, that is greater than. Okay, so this is our KS1 and this is our KS2, because this one is the largest number smaller, and this is the smallest number larger. We draw this up and we see that our P1 is 0.15 and our P2 is 0.1. So then all we have to do is plug in those values into the equation, and we will get our p-value. Now, I'm not going to go through this. We're going to do this exact example in Excel later in the video. So let's say that we have an n of 30 and a KS of 0.104. We find our n row, and then our lowest value here is 0.1315, which means that we can't do any interpolation because it is so low that it's greater than 0.2. Now, in some scenarios, your organization might just care that it's greater than 0.2, but you might want to know how much greater. Are you at like a p-value of 0.8, or are you at a p-value of 0.201? that can be helpful to know because as we remember from the Anderson-Darling, the p-value really is a metric of how closely it follows the normal distribution. And a higher p-value means it follows it much more closely. So it can be good information to know. So because we can't use interpolation, we're going to have to use the approximation algorithm. And the approximation algorithm is pretty simple. P equals the sum of ci times ai, where I goes from 0 to 10, because the 0 cancels out. We have a C0 here all the way up to C10, and then a to the 10th. Now, a is something we're going to have to calculate because it's really not that bad. It's pretty simple. You have these B1, B0, and B2 constants that we have up here, very long decimals, just like the C constants. And then Ks is our Ks test statistic, and N is our sample size. So again, none of this is really complicated. It can just be a pain to type all of these numbers into Excel. If we were to plug it all in with that N and that Ks value, we get an A of 2.90777 and a p-value of 0.546, which is greater than 0.2. So that is awesome. The thing to remember is that we are only accurate to this. So due to rounding, it could be 0.55, 0.54. We aren't super sure. But again, this is a high enough p-value that we are going to be okay. So when we were looking at this, something you might remember from the Ks test statistic and something you may have noticed in the p-value table is that higher values of the Ks test statistic correspond to a lower probability that the data originated from the normal distribution. So that means higher Ks, lower p-value. And like always, for the p-value, we're going to use a critical value, and you should always check with your organization to make sure you're using the right one. For our cases and the general one, we're going to use a 0.05 value for the p-value. That's pretty common. Up to your organization, make sure you check with them. Okay, so here we are in Excel. We are going to do an example of the Lilliefors corrected KS test. Now, this entire document is available for download in the link in the description. I highly recommend downloading it. All of this math is already in here, so go ahead and delete some of these if you want to follow along, or you can just use it. The only thing is, since we are doing the Lilliefors, which uses the KS test statistic, instead of programming all of that, we are actually going to use QE Suite. So if you don't know how to get QE Suite, link in the description on how to get started with your free trial. It performs all of the normality tests we've looked at so far in Excel with one single function. Highly recommend using that, but this is still a great chance to learn. So let's get started. Okay, so the first thing that we're going to need to do is get our KS value. And if you remember, we're going to use the QE Suite function. So QE dot Kolmogorov-Smirnov, and we're going to collect our data. Oops. And I'm going to say return as object and hide my graph. And then I'm going to say .ks. And what that's going to do is instead of returning the Ks and the p-value as the Kolmogorov-Smirnov function normally does, it just returns the Ks value. So now we are halfway there, and all we have to do is calculate the Lilliefors p-value, which is the entire goal of this video. So the first thing that we're going to do is we are going to use our p-table method, so p-value from table. Okay, so the first thing we need to do is get our Ks values at this sample size. So we're going to say index, and we are going to say select this entire down to 50, and I'll explain what this 50 plus is here in a second, but first we're just going to select this. Okay, and then our row number is going to be n minus 3, and that's because we start at 4, so we want to get everything offset by 3, so that 4 minus 3 is 1. That is our first row there, and we are going to hit enter. Oops. And I forget we have to include this for the column number. There we go. That returned our entire row there for the KS value. Let's double check. 1315, 1378, 146, 159, 1848. And we have 146, 159, 1848. Awesome. So That is great, but you'll notice we have this 50 plus here, and that's because the p-value table given to us by a paper by Abdi that uses this. So this is the corrected table. So it took Liliafore's values and just made them a little bit sharper, a little bit more precise, and expanded it a little bit. It goes up to 50. And so we have these equations here, which are already plugged in for you, so don't even worry about it. And that works for any sample size above 50. So what we're going to want to do is we're going to want to use an if statement. So we're going to say if n is greater than 50, then we're going to just select this row. Okay, awesome. There we go. Nothing changed because our n is not above 50. Next, we are going to do this bool row here. And what that's going to do is that's going to tell us whether or not this value is greater than our ks. Okay? And actually, we want to do less than our ks. So if we say is less than ks, we get true. Okay, awesome. So I'm going to absolute reference that ks and then drag this across. And now you can see we know that these two are lower than, these are greater than. So this is our ks1, this is our ks2. So what we're going to do is we're going to say count if, and we're going to select this range, and we're going to say true. And now we have 2. So that we're going to use to grab our p-value. So p-value equals index, and then our array is going to be the p-values, our row number 1, and then our column number is going to be our inflection. So it's going to grab 1, 2. Yep, perfect. There we go. And then we're going to do something very similar. We're going to say index. Again, grab that. And then our row number will do 1. And then column number is going to be inflection plus 1. 0.15, 0.1. Awesome. Looking great. And now our ks is going to follow that exact same format, where we select the array of ks values, and our row is going to be 1, and then inflection. Great. ks2, again, pretty simple stuff, but maybe some functions that you aren't totally aware of yet. Super easy, though. All right, and now inflection plus 1 to make sure we grab that. And now we're going to plug in our interpolation equation. So we know that that is P1 plus, and then we are going to do P2 minus P1 divided by K2 minus K1, KS1, times our KS value minus KS1. There we go. We have a p-value, and in here I'm going to select that. So the reason we did that is because we also want to have the ability to use our approximate value. So this was going to require just a little bit more work to write in these equations, but still not bad because we have all of those constants right here. Okay, so for our a value, we're going to open up some parentheses, and then we're going to say negative, open up some more parentheses, b1 plus n. Close that, plus the square root of, and we're going to say power, and this is b1 plus n squared minus 4 times b2 times, and then we're going to open up another set of parentheses, a lot of parentheses here, b0 minus power ks to the negative 2. Oops, negative 2. Close that, close our square root, and close our numerator. Then we're just going to divide this by 2 times b2. All right, everything looks great. Hit enter. There is our a value. Okay, and now for our p, we are going to then take that. This is going to be a little bit longer, but it's c0 plus c1 times a plus C2 times power a squared plus C3 times power a cubed plus C4 times power a to the fourth plus C5 times power a to the fifth plus C6 times power D12, which is a to the sixth, plus C7 times power of D12, which is a to the seventh, plus C8 times power D12, which is a to the eighth, plus C9, and you guessed it, times power of a to the ninth, and finishing off with C10 times power of a D12 to the 10th. Enter, and there is our p-value. So let's put that in here, and look at that. As we said, it is only accurate to that second decimal, that hundredths place. So if we were to round this, we would get 0.11. And that's what we mean by it's only accurate to that decimal place. As you can see, it at a low p-value can be kind of risky as to whether or not you would correctly reject the null hypothesis. So definitely make sure that you're using the tables when you can. So this use approx we'll get to in a sec. But first what we're going to do is we are going to make sure that we can select between them. So we're going to say if we use the approximate method, then we're going to use the approximate p-value, else we're going to use the table p-value. And right now we don't have, we're not using it. If I were to type in true, true, there you go, it would switch. So now we want to add in some logic that allows us to use this down here to select between the two. So if you remember, we're going to write an if statement. If you remember, we want to make sure that we use the approximate if it is lower than any of these values. If it's greater than the 0.01, we're just going to call that 0 because in that case, you know, that is such a low p-value, your data does not follow the normal distribution. You just have to accept it at that point. And approximating your p-value, you will end up with negative values because you're only accurate to that 0.01 anyway. So it's useless above that. So we're going to use it if it's below. And so if our value is below this 0.2 ks value, we're going to get an inflection of 0. So we're going to say if that equals 0, then we want to return true. Because if that's less than 0, if that equals 0, then we need to use the approximate value. Else we're going to give it false. And there we go. Now if we were to have a ks value, like let's just use that one from our example, 104.165, we end up getting our p-value from the approximate. We get a spill error there, and that is just fine. No harm done. Okay, I'm going to undo that, and there we are back to normal. Okay, but let's say you don't want to go through all of that hassle. We're going to use this, equals QE dot Lilliafor's test, and we are going to select our data, hide our graph, and there we go. Just like that, in seconds we were able to do everything it took us about 10 minutes to do. But that is the Lilliafor's corrected KS test. Soon we will be talking about some comparisons of these normality tests, and we'll really dive into why anyone would want to correct the KS test anyway. So thank you so much for watching. Have a great day, and please do something awesome.